We're surrounded by these incredible structures every single day. Roads, bridges, buildings. We kind of take them for granted. But underneath all that concrete and steel, there's this invisible language, this secret blueprint made up entirely of numbers that's holding the whole thing together.
Just think about your commute this morning. You almost certainly drove over a small bridge or culvert that looks just like this. It feels solid, dependable. It's just there. We trust it with our lives. But have you ever really stopped to think about what it takes to make something so simple look so strong?
And I'll give you a hint. It's not pouring concrete. It's not even digging the foundation. So what is it? What's the absolute first most critical step that has to happen to turn an idea into a physical reality you can stand on?
Well, the answer is you have to create a recipe, a perfect, unbelievably precise construction recipe. A list of ingredients so detailed that it accounts for every single nut, bolt, and drop of concrete in the final structure. And of course, that recipe has a technical name. It's called quantity surveying. It's this super meticulous process of calculating exactly how much of everything you're going to need. Every bag of cement, every ton of gravel, every last steel bar. And then figuring out what the whole thing is going to cost. Let's put it this way. You wouldn't bake a cake without knowing how much flour to use, right? Well, quantity surveying is that same exact idea, just scaled up for bridges, skyscrapers, and even entire cities. It is, quite literally, the master recipe for building our world. Okay, so that all sounds good in theory, but how does this actually work? Let's zoom in and take a look at one of the most common but totally overlooked pieces of infrastructure out there, the humble culvert. So what is a culvert? Well, it's basically just a small bridge. Its whole job is to let a stream or some drainage flow underneath a road. Typically, we're talking about something with a span of less than 20 feet. Looks pretty straightforward, doesn't it?
Well, yeah, it's simple on the outside, but the whole process always kicks off with a super detailed plan, just like this one. This is a top-down view, and you can already see the wild precision involved. Every single piece is mapped out. The main supports, which are called abutments, and these angled wing walls that help channel water and hold back all the dirt. Now this is where it gets really cool. We're going to slice it right open and look at a cross-section. And boom, suddenly that simple structure reveals its hidden DNA. Now we can see the exact thickness of the concrete, the dimensions of the foundation, and this is crucial, the precise location and size of every single steel bar that gives the concrete its strength. And this is where the math just completely takes over. The entire structure gets broken down into individual geometric shapes. You can see in this table, each part, the foundation, the walls, the top slab, is calculated to find the precise volume of concrete needed. And look at that precision, 13.60 cubic meters here, 9.94 there. There is absolutely no guesswork. And it goes so much deeper than that. I mean, we're not just talking about the big stuff like concrete. This page shows the actual formulas used to calculate the length and the number of steel rods needed inside just one part. You don't have to understand the math, just look at that. That's the mind-boggling level of detail needed to account for every piece of that hidden steel skeleton. So, that same painstaking building-by-the-numbers approach for concrete, it applies to absolutely everything. To see how this scales up, let's look at the steel framework for something much bigger, a bridge truss. So here, we're looking at the steel beams for that truss, and it's the same exact game as with the culvert's concrete. The entire steel frame is broken down into its individual parts. You've got the top cords, the bottom cords, the sway bracing. Each part is calculated by its length and its specific weight per foot to get a total weight. And what happens when you add up every single one of those pieces, every cord, every brace, every single strut? You get this, 10,174.4 pounds. That is the exact weight of steel that needs to be ordered, built, and lifted into place. Not a pound more, not a pound less. So why does that exact number matter so much? Why care about the 0.4 of a pound? Well, because it all comes down to money. The total weight gets multiplied by the price of steel per pound, and that gives you your final cost. If you get this number wrong by even a tiny fraction on a huge project, that mistake can snowball into a financial disaster. This one calculation is pretty much the anchor for the whole budget. Okay, so let's zoom back out and ask the big question again. Why? Why go through all this painstaking, meticulous calculation? Why does every single tiny detail matter so profoundly?
Because this process, this quantity surveying, is the invisible foundation of the whole project. It's how you stop budgets from spiraling out of control. It's how you avoid wasting materials, which saves money and is better for the planet. But most importantly, it's what ensures the thing is actually safe. The math dictates the strength. The right amount of steel isn't a suggestion, it's the difference between a bridge that lasts a century and one that fails. And on a practical level, it's the exact shopping list the builders need on day one. So, the next time you drive over a bridge or watch a new building go up, remember this. What you're seeing isn't just steel and concrete. It's a monument to an immense intellectual effort, the thousands of calculations happening behind the scenes that truly brought it to life.
And that kind of leaves us with one last thought, doesn't it? Just look around you right now, at the room you're in, the road outside your window, the city where you live. What hidden math is holding up your world?